Your red sunset survived 40 times more air than your noon sky. Stare at the sun at noon. It looks white. Pure, flat white. That's a lie. That light actually contains every color you can see. Violet at 380 nanometers, red at 700. They all crash into your retina at once. Your brain just can't separate them, so it calls it white. Isaac Newton proved this in 1666. He used a glass prism. A beam of sunlight went in and fanned out into a rainbow. Red bent the least. Violet bent the most. He showed that white light isn't one thing, it's a crowd. Now look up. The sky between you and the sun isn't empty. It's about 60 miles of gas, mostly nitrogen and oxygen, packed with molecules. They're invisibly small but insane in number. 1 cubic centimeter of sea level air holds 25 billion molecules. Sunlight doesn't pass through this gas cleanly. Photons collide with molecules. That's Rayleigh scattering. Lord Rayleigh worked out the math in 1871. When a photon hits a molecule much smaller than itself, the molecule absorbs it. Then it spits it out in a random direction. The light bounces. But here's the wild part. Colors don't scatter equally. Rayleigh's law says scattering is inversely proportional to the fourth power of wavelength. That fourth power does heavy lifting. Shorter wavelengths scatter way more than longer ones. Let's put numbers on it. Blue light at 400 nanometers scatters 10 times more than red at 700. Not twice, 10 times. When a blue photon and a red photon enter the air together, the blue one gets knocked off course 10 times more often. That's why the sky is blue. During the day, sunlight comes straight down through maybe 10 miles of air. Blue photons scatter everywhere. They fill the whole sky with bounced blue light. Blue can't stay on a straight path. Red punches through and hits the ground intact. So at noon, the sun looks white. Most of its spectrum still reaches you. The blue depletes a bit, but you won't notice. The sky around the sun turns blue because that's where the scattered blue went. The system works. Then the sun sets and the geometry changes. The sun drops lower. Its light doesn't come straight down anymore. It enters the air at a shallow angle. It skims across the Earth's surface like a stone across water. That angle changes everything. At noon, sunlight passes through 10 miles of air. At sunset, when the sun hits the horizon, that same light travels through 40 times more air before it reaches you. Not twice as much. 40 times. Think about what that does to scattering. Blue light already scattered 10 times more than red through 10 miles of air. Now it has to survive 40 times that distance. Blue photons don't stand a chance. They scatter out of the beam immediately. They disperse into the sky around you. By the time that light reaches you, the blue is gone. The green is gone. Even the yellow gets stripped away. What's left? The stubborn end of the spectrum, orange and red. These wavelengths are too long to knock off course. They are the survivors. When you watch a red sunset, you don't see the sun's true color. You see the wreckage of its spectrum. The air filtered out everything fragile. Red is what remains when everything else scattered away. A sunset isn't a color. It's a deletion. This also warps the sun's shape at the horizon. Atmospheric refraction bends light more at lower angles. The sun's lower rim bends more than the upper rim. The sun looks flattened, squashed into an oval. You literally watch the air distort it in real time. Not all sunsets are equal. Color intensity depends on what's in the air. Clean, dry air gives you a pale yellow sunset. Add dust or water vapor, and the colors deepen. These larger particles scatter light differently. It's called scattering. It hits all wavelengths evenly and enhances the reds. That's why coastal sunsets look amazing. Salt spray and humidity put larger particles in the air. Rayleigh scattering from molecules mixes with scattering from aerosols. You get a richer, deeper palette. The physics layer up. The sky becomes a battleground of competing mechanisms. Volcanic eruptions make the most unforgettable sunsets in history. Krakatoa erupted in 1883. It shot sulfate aerosols 30 miles high into the stratosphere. Those particles circled the globe for years. People across Europe and North America saw blood-red skies and fire-colored twilights for months. The painter Edvard Munch saw one of these Krakatoa sunsets in Oslo. It shook him so much he put it in the Scream. That iconic orange and red sky behind the screaming figure isn't imagination. It's a documented atmospheric event, a volcanic sunset painted from life. A number hides in all of this. Sunlight in space has a color temperature of 580 Kelvin. That's the sun's actual output. By the time that light reaches you at sunset, the temperature drops to 2000 Kelvin. You receive fundamentally transformed light. Look away from the sun during sunset. You'll see a pinkish band rising in the east. That's the belt of Venus. Sunlight scattered by the upper atmosphere. It sits above the dark blue band of Earth's own shadow. You watch the last light and the first shadow at the same time. Then there's the green flash. For 1 or 2 seconds, just as the sun's upper rim dips below the horizon, you might see an emerald flash. The atmosphere acts like a prism. It separates the sun's light into a tiny spectrum. The horizon absorbs the red and orange. The blue scatters away. For one moment, green is the last color visible. It gets stranger. On Mars, the sunset is blue. The Martian air is thin, mostly carbon dioxide, and full of fine dust. This dust scatters light differently than Earth's gas. On Mars, dust scatters red light more than blue. The daytime sky is butterscotch. At sunset, it turns a cold blue. The same physics, inverted. A sunset's color tells you what's in the air, not just on Earth or Mars, anywhere. Astronomers use this to study exoplanets. When a planet passes in front of its star, starlight filters through its atmosphere. Astronomers look at which wavelengths survive. Then they infer what gases are there. Every sunset you've watched was a live spectroscopy experiment. The air was the sample. The sun was the light source. Your eyes were the detector. The red you saw was data. It told you the air's composition, the sun's angle, and the dust or moisture levels, all encoded in color. The chain runs like this. White light leaves the sun and enters the air. Gas molecules scatter the blue. The sun drops lower, extending the path. More blue scatters away. Green follows. Yellow fades. Red survives. You see red. The sky around you glows with scattered remnants. Then it's dark. The whole process takes 30 minutes. It starts when the sun touches the horizon and ends when the last color fades. During that window, the air separates visible light in real time, just like Newton did with a prism in 1666. Except this prism is 60 miles thick. It's made of nitrogen, oxygen, and water. Here's what stays with me. You've seen hundreds of sunsets, maybe thousands. Every single one used the same physics, the same scattering, the same filtering, the same wavelengths fighting through the same molecules. But the air is never exactly the same twice. So the colors are never exactly the same twice. No 2 sunsets are identical. No 2 moments of air are identical. Temperature, humidity, dust load, cloud cover, angle, season, every variable shifts slightly. The output shifts with it. You watch a system with fixed rules but infinite outputs. Next time you see a red sunset, you'll know what you're looking at. Not just beauty, not just air, a live demonstration of quantum electrodynamics. It plays out at the speed of light, 93 million miles from its source, filtered through a 60-mile lens of gas that you breathe. The red light in that sunset is the oldest, longest, most stubborn part of the solar spectrum. It refused to scatter. It traveled straight while everything around it bounced and diffused. Then it found your eyes. That's a physics lesson, written in the only language the universe uses for everything. Light. Next time you see a red sky, tell someone why. Then subscribe for more things worth knowing tonight.